Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
In this video, we will look at the tools that we need to analyze motion in one dimension, which is just moving along, let's say, x-axis, for example. First, we look at motion with constant velocity, and then we'll expand to constant acceleration, and in the end, we'll finally look at the motion when the acceleration also changes. But the simplest form of motion is, of course, that of constant velocity. So let's have an expression for that. So x is just the position of the object on the x-axis at any given point in time. And of course, when we have constant velocity, v, 0, that's the initial velocity, and x means that it's along the x-axis. After t seconds, that is our new position. So this is the rate that we increase our distance from the origin. We can also have have some initial position, let's call it x0. We don't necessarily have to start from the origin, so in that case we have x0 here. And most of you have probably already seen this, what happens when we have also acceleration. So when the velocity is not constant anymore, we add another term, and that is due to the acceleration that increases the velocity constantly. So that's half times acceleration a times t squared. This is one of the more useful ones that will help you solve a lot of problems. And if we next look at the velocity, the simplest case when we have constant acceleration, so we can always have some initial velocity along the x-axis like this. And now if we have acceleration, that means that the velocity increases at a constant rate, and that rate is acceleration. So after t seconds, we have added to the velocity with the amount of acceleration times t, and this is of course along the x-axis. On the first two rows of this table, you can see the equations that I just presented to you, and by combining the two, we can get the third and fourth one as well. So this box is a nice little cheat sheet that will allow you to solve any quantity on motion with constant acceleration, depending what quantities do you know already. So for example, in the third row, we don't know anything about the time itself, but we know what is the acceleration and what is the position of the object, and that in that case we can calculate the velocity. And this table has all these combinations for all the quantities one would like to solve. And then again, a compilation of formulas like this gives only a superficial understanding of the underlying physics. And to fix that, let's have a more in-depth look at how velocity and acceleration and position in fact play together in motion in one dimension. I shuffled things around a little bit to make room for these three graphs. What we have here is the position x on the y-axis as a function of time. So if you look at the blue curve, that is just a manifestation of this formula. In fact, it is parabolic function, as is evident from the fact that the t is of second order. So, but what we are trying to do in this first figure here is to calculate the average velocity while we are moving from point 1 to point 2. How do we do that? So what is average velocity? It is, of course, the distance covered divided by how long did it take. And in terms of the graph, what we see here, it's in fact the rise over run. So basically the slope of the curve containing the 2 points. And in the second graph, the point 2 has been brought closer to P1, so there's a shorter period of time between these two instances. But the same thing applies. If we calculate the rise over run, we get average velocity going from point 1 to point 2. Now the interesting thing happens when in the graph C, when the point 2 coincides with the point 1. So basically this means that the time interval between these two instances becomes 0. So we're talking about instantaneous velocity, like it's said here on the graph as well. So by calculating the slope at one point, in essence we are drawing a tangent to the curve at that point, and evaluating slope, we get the instantaneous velocity. And what does this mean algebraically? So let's do this. So like I said, it's instantaneous velocity, so it's velocity at some point in time. So it's still delta x divided by delta t, but at the limit, that's the limit when the delta t approaches 0. So the time interval is infinitely small. And what is this? Well, this is just the definition of derivative of the displacement x respect to time. We can do the same thing with acceleration, in fact. So instead of having x versus t, we have a velocity versus t. And we can draw the same slopes and graphs and tangents, and we get the result that the acceleration is the limit of when the time interval goes to 0 of change in velocity over change in time. And again, this is now the derivative of velocity respect to time. And we can see how this works. So let's look at this expression here. So we are claiming that if we take the derivative in respect to time, we should get the velocity. So let's do that. So we have d of everything inside so that's just a constant, so that gives 0, and oh, there's t missing there, like this, and v times t, derivative of t, we get only the velocity term, and then when we take derivative of this one with respect to t, we get 2 times half at, which is just at. So derivative of x with respect to time is in fact this expression, which is same as v, like we expected. And now if we differentiate this result respect to time, so we have d of whatever here, we have velocity plus the acceleration term. Now the velocity term is constant and we only have this one, so derivative of at respect to t is just a So we have constant acceleration. And this makes sense because we are talking about constant acceleration to start with. So here you see how this works. So if we have expression for the position, by taking derivatives, we can get the expression for velocity and acceleration, even in the case that the acceleration is not constant. So these two formulas are far more universal than the ones that we have collected here. And we'll take this one step further in the next slide.